4 o'clock, perfect timing. And how's our... A little bit better. Okay, so welcome back, everybody. Just I thought I had this open. Quick reminder that, let's see, so your in-class assignment was due the 31st, which was Sunday. And if the couple of you remaining that didn't get that in still want to turn it in, I will still accept it. But that was getting up and running with your Google Cloud site. So I was curious, before we dig into the actual lecture, does anybody have any questions or issues with the Google Cloud page? Or the server in general, I suppose. I just want to make sure that you're all up and good with that. And like I said, I saw that pretty much everybody turned it in. If you are struggling and you need some detailed help, please feel free to drop by the office hours. The only reason I'm asking is that it can be a lot to take in if it's the first time you're using a cloud environment. Um, I'm honestly not sure what you all experience in some of your other classes, but when I was at Oakland, there was a lot of people using like DigitalOcean for hosting websites and writing code and stuff, and moving to Google Cloud kind of makes sense. But if you've never used a cloud provider before, there's there's a lot there, and it can be overwhelming. Still as overwhelming as I'm putting stuff together for a cloud course. But if everybody's good, I'm not seeing any messages pop up, so I will assume everybody's okay. Again, the whole purpose of that server is just to have a web server for you to put your content on. So you're going to be doing all your homework assignments and labs and all that. You'll be putting them up there, so get comfortable moving them around. And then you're just going to send me a direct link to your file. And again, what kind of makes this nice is that if you're struggling with any of the assignments, just send me a link to your web page, right? Upload the file that you have to your server and say, hey, take a look at this. And then I can just open up your source code and see what's wrong, right? Don't have to mess around with copy and pasting code or screenshotting. I can just look at your raw files, which is nice. And then again, later on for the one assignment that we'll be doing with models, you're going to need that server. So good thing that, again, everybody's quiet. That's good. One other thing I kind of wanted to show you, and this has really nothing to do with class. I just find procedural generation fun. I popped this into the Discord channel, but I made a couple of updates here. I have way too much fun playing with procedural generation, and there's this great website called Red Blob Games. I don't know if any of you have ever played Realm of the Mad God. It's like used to be a Flash MMO, now it's a Unity MMO. But this person who did this blog actually did the map generation for that game. And let's see, is this it? Yeah, basically he has a whole write-up of how to generate worlds just using noise functions, which is something that if you're interested in, could be something that you could play with later on for, say, term project assignments or personal fun. But anyway, I was playing with this, and this is in that p5.js language, which is basically a layer above WebGL, and it abstracts out all the horribleness of WebGL. But I'm just kind of changing the direction, hitting space. Let's say that I want to use this to generate a world. I've got to have it moving right now. Code's not the prettiest, but like just based on some of these sliders here, I can kind of play around with world generation. And then, if I liked this setup, I could say write the array out. And here are all the values that go into constructing this map. And like I said, I have fun with this. There's a ton more you can play around with this, but I wanted to learn a little bit about P5 because I saw a ton of people using it, and I've never used it. And it turns out it's really easy. And if anybody's interested in this code, I don't know if you are or not, the coding train. Okay, yeah, that'd be interesting to check out. I found it on there's like the January tag on Twitter, people doing procedural generation, and they all seem to be using P5. So I thought that was kind of neat. But again, I like to kind of show you all what I'm interested in. You can feel free to ignore it if you think it's absolutely awful and boring, um, since it's not strictly what we're doing with WebGL, but it's a layer above. And just to kind of give you an idea of what that map is being generated from, it's all generated from a noise function. So basically, I generate a big array of noise values, and based on the algorithm you pick, they could be more continuous or not. And then you apply a threshold to it. Anything that is, say, less than 0 is water. Anything less than 0.2 is dirt. Less than 0.4 is grass. Less than 0.6 is snow. And then you can just like draw to the screen what you're seeing there. Yeah, I get a kick out of it. Like I said, bit of a diversion, but if anybody's interested, I can send some stuff along. Actually, that's what I wanted to do, because let's see, Red Blob, I wanted to pop this in the chat because I think it's cool and I get to inflict my interests upon you. That's my prerogative as a professor. So yeah, if it's just of interest. If not, think of it as a, hey, this isn't my email. I updated the date and some stuff, but not my actual email. Shameful. Okay, so first thing to talk about today, I have put up your next homework assignment. You have until, promise I'm going to keep one tab open for once, January 9th or February 9th. That is a week from today. Basically, you're going to be looking at the Sierpinskiing gasket fractal, and you're going to be modifying it. So what that's going to be doing is basically you're going to be generating something that looks kind of like this, and you're going to be doing it algorithmically. So basically you're going to generate a triangle, and then you're going to start subtracting things and doing recursion. And there's the code there to really, all of this code is available. You don't have to do this from scratch, but you have to modify it, and you kind of have to understand how it's all working together. And what you're seeing here, these are all points, so no triangles. This is all generated from point data. If I zoom in, it's going to look super blurry, but all just pixels. GL points. And, I should probably show you all the assignment too, otherwise nobody's going to know what the heck I'm talking about. And it is, where is it? It's in Google Drive. It's not there. Sorry, I promise talking to yourself is not as bad as it sounds. All right, here we go. Basically, none of you have had a lab with me yet either. I've given you in-class assignments, but it's kind of worth talking about because, again, you don't know what I'm looking for. For these assignments, it's kind of a handheld lab walkthrough kind of thing. Plus, I want you to do this thing at this step, take a screenshot and paste it in the questions at the end. So I have you downloading the repository if you haven't already. Open up the Sierpinskiing gasket example, modify it so that you're tagging it with your last name, make some changes, show me what you did to make this change happen. Then I want you to flip it. Show me what you did. Again, see this red and red and bold. Copy the code you changed into question 2. So what I'm going to do is I'm going to come down and grade, and I'm going to see, hey, where's question 2? What is your answer? Make sure that you are good. So, up. There it is. Scroll down too far. So just make sure that you update the report at the end. And I've got some questions for you here. Should be pretty straightforward, honestly. Last one, create a portfolio website. So you did the in-class assignment to get your page set up. I want you to actually turn it into a real website where you're going to put links to all of your assignments up there. So basically it's going to look something kind of like this. Make it as pretty as you want. If you go above and beyond, I'll give you extra credit for making it pretty, basically. I noticed some of you already started throwing some nifty things into your Hey, This Works page. So just make sure you read through the manual, get it started early. I'm more than happy to help you along the way if you're struggling. If you ask me on February 8th February 9th at midnight, I probably won't help you, but I'm more than happy to help out if you look into it early enough, basically. So, homework due a week from today. Read through it. Any questions, please feel free to ask them. I'm more than happy to help you. Okay, enough preamble. What we're going to do today is we're going to put everything together into a full program, and we're not going to do a triangle today. We're going to do a square. What does it mean to do a square in OpenGL, WebGL? It means we're going to draw triangles to make a square, right? The only primitives we get in WebGL are points, or lines, or triangles. So we're going to make them with triangles. And what do we have to do with the square? We basically are going to be defining 4 points, and we're going to tell WebGL draw triangles from these 4 points to make it look like we're drawing a square. But to do that, we're going to talk about Glsl, and then we're going to apply that to our WebGL thing. And now Glsl is something I haven't talked about yet. That is, go away pointer. That's just going to be your OpenGL shader language, or shading language. So the code that you're writing in those in those vertex shaders and the fragment shaders, that is actually Glsl code. It looks very C-like. It's taking a note from OpenGL, basically. So let's give you an example of the chain. So I know some of you said you have seen OpenGL code before. What we have here is basically their kind of pipeline-esque approach to taking something from your application program and sending it to the graphics driver. Right? We have the application that you write, so we're going to make our various function calls, glut, gl, glew, depending on what we're drawing. We have some extra libraries in there along the way, but basically it's going to be packaged up and sent to the graphics driver. Right? So application, APIs/libraries, driver. In our perspective here, we have a little bit of a different approach, and you kind of know this already, right? You have your browser, which is going to maybe talk to the web server, depending, right? If you're not running a web server, you can kind of hide this aspect, but you're all running on Google Cloud, you get a web server. Browser requests a URL, it's your web address. Web server sends you back a web page. You're going to get HTML and JavaScript files. Your browser is then going to take the underlying engine. It's going to parse out the HTML. It's going to parse out the JavaScript. The JavaScript engine's going to realize, hey, this is Glsl code. We have to compile it down to GPU code. And then that gets sent to your canvas, which is, again, that element that we're putting out with HTML, right? And in there, we're going to have a frame buffer. Now, this frame buffer is where you're drawing data to. Right? Again, we talked about having a buffer that we're going to be sending data out to, right? To send it to our display. That's what we're drawing in WebGL here. So slight differences. It should make sense. OpenGL is an application-based program, right? You're generating binary files, executable files with OpenGL. WebGL, we're doing web pages. And the other interesting thing too with WebGL is it is based off of the embedded version of OpenGL. So you don't get the full power of OpenGL in WebGL, but you get the very performant aspects of it. Basically the things that are intended to run on like low profile systems, those are in WebGL, but you don't get everything that OpenGL can give you. All right, so that's kind of the little high level there. One of the things that we've talked about in the past too, I said, hey, does anybody know how games are programmed or how animation's handled? Right, I said, at that point, there is this forever loop. It's that while one or while true loop. In WebGL, we have that as well, except it's going to be a render function. And you've all written this already, right? You wrote your WebGL code. You have your, let me pull up let's pull up the gasket just for funsies. If you remember, we have this function render, right? This is what is sending the data to the graphics card. We have our GL clear to clear a canvas, gl.draw arrays, and then everything we've done so far is with triangles, but you can do points, you can do lines, right? There's multiple options here. This is your forever loop function. Now, the way we've been using it so far is it is a while true and then bail out once that first loop is done. And the reason why is that we are never calling this thing again. All right, so if you look at our standard WebGL program. There's a lot more in here because again, it's a little bit more complicated than what we've been looking at. But we have our window.onload equals function init. So this is being called when your browser window, everything's initialized. Basically, the canvas is there for us to play with. We don't have to worry about, hey, does it exist yet? We're just going to let JavaScript handle that for us. We have our main function here. We have all of our WebGL stuff. You see your initializing. Here we're setting our buffers, our fragment shader, our position. Well, I'm sorry, just our positions here. No colors really. And then we're going to call render. So we basically have int main, set up the program, call render, done. There's no loop here. What we have to do for this perspective is that we have to recursively call render, basically. Now, everything we've been doing so far is static. Dynamic programs, we're going to call render more than once. And how we handle that typically in OpenGL or SDL or any standard library is going to be with a while forever loop, right? So your while true loop. In JavaScript, we don't really have to do that because that's actually going to lock up the browser if we do that. And we don't want our browser to lock up. We're not going to do this today, but I'm just kind of giving you a preview. If we want animations, if we want, user interaction with our canvas, right? I want to click something and then something happens. There's a lot of things that go into that as well. But we want to call render recursively, and basically all that's going to happen is we're going to set a callback function. So we're going to have render call itself over and over and over again. And based on how quickly it calls itself and how quickly it can call itself, we'll have our frame rates and all of that kind of standard video terminology that you would typically have. But instead of a while true loop, we're going to just set a callback. It's going to be, I don't remember the exact JavaScript function call off the top of my head, but we're basically going to just set it to call itself. And we could say like every X milliseconds, call yourself. Or based on an event. So if we don't want it to be processing animations, it can just be sitting there and then say once the user does something, then we trigger the render to be called again. Thank you. Request animation frame. I was thinking like window.set event listener, but yeah, request animation frame is exactly the one that we're looking for. Thank you. But yeah, that's what we would call. And with that, that function there, Philip, basically you set it with a time as well when you want that to happen. Okay, but yeah, we'll be getting to that, don't worry. If you want to, I guess I should say, if you're bored with static stuff and you want to get into that, and why does escape no longer exit full screen? You can go to the, go away, project that I abandoned a while ago. You can go here, and then you can look at one of the animated programs and just look at the source code for this, if this is something you're interested in. Yeah, like here you have request animation frame, and then without a time on there, it's just going to go with whatever the default of the browser is going to be. But you can lock frame rates and stuff like that too. All right, back to our talk. So our function format has some conventions that are going to be useful for you all to know. And most drawing languages will have something like this. But it's kind of good to follow or understand what the convention is so that you can look at the documentation and say, intuitively, I know what this thing is doing. Right, so we have this GL. We should hopefully know this by now. That's the WebGL program that you've created using those libraries and modules. It's going to have various methods and attributes attached to it. So let's say here we have our uniform 3F. Basically, uniform is going to give us a vector or an array of some variables. The number here is going to be the dimensionality of this thing that we're generating. And then the designator here is what variable type it is. So here we're getting a uniform. It's 3 dimensions, so you would expect an X, Y, and Z, and then you'd expect all of the variables inside it to be floats. You could change it to be 3FV, and then you get a vector instead of an array. Just kind of depends on what you want to do with it. And really the only reason I'm bringing this up is that you're going to be seeing a lot of very similar looking functions. Some of them might be ints. Some of them might be characters. So it's kind of helpful to just quickly be able to understand that. We had our vec3s and vec4s. Those had no data type on them because we didn't strictly care what they are. But we did see that they're 3-dimension, they're 4-dimension, they're 2-dimension, and that's vec2, vec3, vec4, right? This stuff will come in a lot later. I just want you to be aware of that convention. All right, so some of the constants that we have to deal with in WebGL. In OpenGL, this came from your pound includes. If you're doing it in C++, if you're doing it in Java, it's coming from your imports. But these are going to be your general constants that you set to configure OpenGL, or that you want to use from OpenGL. In WebGL, we have very similar notions as to what OpenGL had, except it's going to be tagged to the GL object that you create. Again, when you instantiate the WebGL program, you get this GL variable, assuming you named it GL. The variable names for these constants are going to look very similar to what is in OpenGL because, again, it's derived from the same language. So if we want to set our application to use 3D, we would need to set the GL depth test flag in OpenGL. In WebGL, it's the same thing, except it has GL dot on it. And again, we're not going to use every single constant. We're not going to necessarily need to. Where we will, I will show you what we have to use. But basically, just be aware that they're going to need that GL dot in front of it. Or again, whatever you called your program name. You could call it WebGL program dot, and then you'd have depth test, color buffer bit. And again, depth test, this is setting a Z buffer. So basically you're getting a 3rd dimension. Color buffer bit, hopefully you remember that's how we set the color of our background, basically what we're clearing our background to be. And there's a ton of them out there too. Here's just a couple. All right, a few more things before we get into some programming. One of the differences between OpenGL and WebGL is that everything that we're doing in WebGL is shader driven. And what I mean by that is that we're not going to be doing any drawing using the CPU. We're going to force everything to be in the shaders. So those of you at the beginning that asked, are we doing shaders? And I said, absolutely, you're doing it right now. Everything we're doing is in shaders. And what you're learning here, you can take and apply to OpenGL to whatever graphics language you want. Everything we're doing is shader driven, right? So that's kind of nifty that you get that sent right away, or you get exposed to shaders right away. But if we're doing shaders and everything's a shader, what's the purpose of the application? And if you remember from before, the application's actually kind of all the JavaScript code we're writing surrounding that shader code. Basically, everything there is to take everything you're doing for the shader and pack it up and send it over to the GPU. So we're defining vertices in our shaders, we're defining our fragments, which is right now just colors, but we can do a lot more with that in our fragment shaders. The JavaScript's massaging it and getting it in the correct format and getting it ready to go to the GPU. And then once we call that render function, which has gl.drawArrays, that's what's actually taking everything that's been neatly tied up, sending it to the GPU in a format that it needs. So that's basically kind of the point that we have here. Yeah, and again, applications are JavaScript code, shaders are the shader code, the HTMLs are pretty little front end that we have. Okay, good so far, I hope. I assume you'd all be interrupting me if we had issues. Let's talk a little bit about GLSL and then we'll talk about squares. So GLSL, again, this is your shading language, OpenGL. So GL is graphics language, graphics library shading language. If you've ever used C or C++, you should feel right at home. We have matrices, we have vectors, where I guess you're coming from C, you don't really know what vectors are without implementing them yourself. These tend to be 2 to 4 dimensions. Overloads are fine. Constructors are there. They're C++ alike. So again, fairly standard programming concepts here, nothing too crazy. WebGL is going to compile it, it's going to link it, it's going to talk to the shaders. Again, we're going to package it up to send to the GPU. Pretty straightforward. We're not going to do a super deep dive into Glsl. We're basically just going to be using it for our own ends as we need, and you'll get exposed to all of the different things we can do with it. For Glsl, we're going to be packaging it up in the HTML file, so we're just going to put the shaders right in there, but there's nothing stopping you from having them as separate files and including them if you want to as well. If you look for WebGL examples on the internet, a lot of times the HTML page is very barren. Your JavaScript application is there, but then people will link in their shader code. So that's something that you can do if you want, but for this class, we're not necessarily going to need to do that. Alrighty, let's do some squares. So I've got 3 images here. I've got a square, a triangle, and a shape. So we'll call this a polygon. Can anybody guess which one is which? I was going to say which one's the triangle, but they're all based on triangles. I guess without any information, that's a question. Yeah, they're all triangles. There we go. So I've got the link here to the code in the slides. But let's, I've got some slides that are going to walk us through the code kind of hand by hand too. I'm not going to type this all out because basically not much will have changed from triangle.js to this. But I've got it there if you want to follow along. Okay, so we're getting into the full program here. And actually, I'll be right back. I left a note that I had for this upstairs. Give me one moment. Take this time to chat amongst yourselves. BRB. And Rex. Sorry, forgot my professor note sheet. Nobody got in trouble while I was away, right? Nobody was flinging spitballs around the room. All right, paints we're gonna need in a few. Sure. Thank you, Philip. I gotta have fun with this, otherwise it's not gonna be a fun class. I haven't even heard of King of Staten Island, though I'm way out of the loop. Alrighty, we're back. Okay, so for a full program, you've all done that already with Triangle.js and Triangle.html, right? Maybe it dropped off the face of the planet. Okay, so you need your HTML page, you need your canvas, you need all the support files. So HTML is going to link everything together. We have to define our shaders, and then we basically have to set up our application. Oh, no worries, I told you to sidetrack us. That's fine. What fun is a class if you can't sidetrack your professor, honestly, and everybody else? I think I was probably a terrible undergraduate for everybody else. I think I was one of those people that always interrupted to ask questions and bother my professors just to see if I could get him off topic. So any interruptions are probably well-deserved. Alrighty, that's what I do. Yes. It's fun when I was an undergrad, I thought I was probably funny or hilarious, and I was probably annoying as F to the professor. And I feel bad about it now. Alrighty, so square.html. So we'll talk about this here. So this is going to look very, very familiar to all at this point, right? Straight up HTML page. Here we have our 2 shaders. We have our Vertex Shader here. We have our Fragment Shader here. And you know what? This is gonna keep popping up on me. Let's do this. All right. Vertex Shader looks very, very similar to what we had before. Fragment Shader, similar to what we had before. Actually, probably identical, except now we're passing in white for the color. So that's the only real difference here. And if you remember from last time, this is called a pass-through shader. right? Because all we're doing is relaying information onto our application. We're not actually doing anything. When we're animating, we can update our shaders, right? This is the very bland and boring shader code that we have right here. We can do so much more, but we're just passing through because we're just drawing basic shapes, right? So we have this. What is this doing for us? I guess important things to care about in here. This GL position, GL frag color. These are two variables that we're defining, or sorry, that are already defined for us, but we're defining this V position variable. And if we were defining multiple colors, we would call it like V color and F color, if you remember from last time. But GL position is what we're sending our vertices to. GL frag color is what we're sending our colors to. And if you look further down the line, we're going to be getting that from here in our association of our shader variables to our buffers again. So we're looking for V position, and the color we're just passing through. So again, these variables are known to WebGL. They're trivial programs, trying not to oversell that these are basic pass-through shaders, but this is a full program that is getting compiled and linked by the browser, the WebGL engine under the hood there. One other point too, so we are setting the precision of these variables in our shader, specifically in our fragment shader. Again, if you remember this little line, precision, medium P floats, we can change that to multiple levels of precision. Medium P is fine. If we need more precision with our floating point variables, maybe we are doing like some kind of fluid dynamic simulation or something like that. We'd want more resolution, so we could bump up that value if we need to or not. Just depends on what you want. Okay, the rest is square.html. We have our libraries here. We have a link to our script, which is again our application. We have our canvas, and then that's pretty much it. No real changes to triangle.js except for the name of these things, right? And keep in mind when you're going to do your lab, I have you renaming gasket1 to gasket1 dash your last name. Don't forget to update that here because you're going to start making changes to it and you're not going to know why it's not showing up. Good chance you forgot to update this variable right here, or this file path right here. So just make sure you do that. All right, we should already know this too already, but I just want to kind of refresh you on that. Webgl Utils and its shaders, MV, utilities for setting up WebGL, matrix vector package. Always make sure you have them, otherwise your program's not going to work. If you do not have them because you're cool, that means you're setting up WebGL all by yourself and you're going to have a miserable time. So make sure you include those. Then square.js is going to be our application. I should say this though, if you are going above and beyond, maybe you're done with class and you still want to play with WebGL, the other libraries like Babylon or 3.js or any of the WebGL drawing libraries, there's going to be equivalents in there, but you're going to have to change your function calls to match whatever their API is. We'll look at Babylon and those later, closer to the midterm probably. Alrighty. So square.js, this is our application, right? We have our GL variable, this is our WebGL object, and we're going to define our points, where these are going to be actually our vertices again. We get our canvas object, we set up WebGL, again, boilerplate code for us at this point, and then we're going to set our vertices. So we have 4 vertices here, and I'm going to inflict upon you my horrible drawing skills. And yes, I do have a tablet, and no, I am not good with it. It's actually less painful to watch me do this in Paint with a mouse. Okay, so these hashes are all 0.5. Okay, so 0.5, negative 0.5. Let me toss a X, Y, and I'm gonna guess nobody can see that because it's tiny, but it's good enough. All right, now I'm gonna need our pointer there. So we have these 4 vertices here, right? Negative, 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 positive, 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 negative. So I'm going to go ahead and just draw these in right now. And we want that bigger, please. Size, that's the one we want. 0.1, or sorry, not 0.1. It's going to take a second to draw these guys in there. So here's our 4 vertices that we're defining. And I just want to make sure I get the order right. So negative, negative, so this is going to be 0. Negative, positive, this is going to be 1. Positive, positive, this is going to be 2. And here we have 3. Nobody, I guess, can you guys see the numbers in the chat? 3, please. E, yeah. Yep, good. Okay, I'm going to be doing some drawing with this. Kitten mittens, hello, okay. So, 4 vertices. Again, our axes are 0 to 1, if you remember. So everything that we do in WebGL is going to be between -1 and +1. And you're going to say, hey, that's an awful resolution. What if we want it to be zoomed in or out? When we start playing with the camera, we'll be scaling these coordinates. But until we get to that point, everything is within this range. That does not correspond directly to pixel ranges, I should mention too. Basically, you just have to kind of play around with it until you get a feel for it, I suppose. And it feels kind of weird having a very static axis for now, but we'll get there, don't worry. All right, so I've got my points there. We will come back to that in a moment. So, other things with WebGL. In our first examples, we did not use the onload code, if you remember, if you kind of zoned out at that point. Onload is going to help us load everything in first and then execute our WebGL code. Everything is going to crash and burn if we put our WebGL code at the top, load in our JavaScript, and the canvas hasn't rendered yet. So if you maybe remember from any old web programming class, maybe your professor made you make a web page, maybe you're an expert and you already know this, but these pages are loaded sequentially from the top down. So the browser is going to read the HTML file line by line by line, right? So it's going to read this. It's going to say, okay, here's shader code. Let's compile that. Okay, let's pull in these libraries. Here's your application. We're going to load it in. Then it's going to load in the body and the canvas. And if you don't have that window.onload code, it's going to try to call your canvas before it is actually instantiated on the page. So that's why in our first example, we put all of our scripts down here after the canvas so that it would actually be in memory already. But in here, we have this window.onload equals function init. Mentioned this earlier, but this is a very specific JavaScript call that you make to make sure that everything is in memory. And if it's not, it will break and it will tell you, hey, we can't find the canvas, or similar based on whatever your JavaScript engine's telling you. So we have window.onload. That's going to save you a lot of hassle if you use that. All right, so we have that. Canvas is going to become a WebGL element, so you can set the context of a canvas. This is an HTML5 thing. Basically, you can tell the canvas what kind of drawing surface it's going to be, whether it's HTML5, whether it's going to be SVG drawings, where you just give it points to draw, or if it's a WebGL object, which you are setting. And again, you're setting that here. Canvas equals document.getElementById, GL canvas. Set that to be a WebGL object. The canvas is a pretty nifty element, I should mention. All right, all of our vertices are going to be vec2 that we're playing with here. And we should see that here, vec2, 2 dimensions, x and y. Our JavaScript arrays are a little bit different than your standard C and Java arrays. They are actual JavaScript objects, meaning that they have methods and they have properties. So if you've ever done any web programming, and if you've ever done any JavaScript, you might know all those cool little things you can do with JavaScript vectors, or sorry, JavaScript arrays. Those are all available to you here. So you can get the .length property, you can do the .index of, you can do contains. So all of those things that you want to do in standard JavaScript, it's available to you here. That's one of the kind of cool things about the fact that this is in the browser. You can take advantage of HTML and JavaScript on top of WebGL. And is the .length property unique? No, I mean, you can do that in Java and C++ and all that stuff, but it's available to you here too. Last but not least, values are in clip coordinates. Does anybody know what a clipping plane is? We talked about this last time. I just want to make sure you remember. Let me pop that into chat too. What is a clipping plane? Crab dancing. Plan? Oh my god. Plane. Think he's going to be cute with the emojis, and then he can't spell plane. I don't remember. Good. So the clipping plane is the drawing area. So if you have your canvas, yeah, it defines what you can see with the camera exactly. Yeah, what's displayed. Again, this was the example. My clipping plane, and you can't see it, but it's my face on the screen here, right? It's my camera window. If I do this, I'm outside of the clipping plane partially. This half of my face is not being drawn. This half is. So yeah, clipping plane is something that we'll be talking about. Basically, anything outside of that -1 to 1 range will not be shown. Let me show you really quickly here what I mean. So let's go to our gasket. F11, not that one. So here's our gasket, right? This is all in our clipping plane. And again, this is your homework. If I update our vertices, let's make this -1.5. Okay, so I'm setting the left bottom vertice outside of the clipping plane. That's not what I wanted to do. Because it's doing fun things with recursion and all that, let's do that in our square. So here's our square. Right now it's set to be a triangle. All right, if I change this to be -1.5, it's going to look like that. Didn't work with the Sierpinskiing because we're algorithmically updating all the variables, but you see that the leftmost bottom vertex is now off screen. It's being clipped out. I'm drawing a triangle here, and I'm not actually spending any resources to draw outside of this clipping plane. That's like in those, in any of those games that you may play where stuff kind of like pops into existence, or maybe it smoothly comes in. If you don't see it, it's out of the clipping plane. If it's inside your clipping plane, you can see it. Last time we called it the clipping volume because there's like a front and a back, and there's a kind of a pyramid-ish shape. Not really pyramid, it's more of a pyramid with the top cut off. But yeah, that's our clipping plane. So save, refresh, there we go. Present. Okay, so yeah, clipping plane. All right, Square.js continued. So everything here should look pretty similar, right? So we define our vertices. So I've got some commented out code here that we'll play with. But for vertices, that's what I've got drawn here, if you remember. So 0, 1, 2, 3, 0, 1, 2, 3. And I'm saying 0, that's the index into the array. We're going to configure Webgl. Again, define our viewports, define the clear color. Again, here the clear color is black since it's all zeros. And we can fully see it. The alpha value is not set to be see-through. We're going to load in our shaders. So again, Vertex Shader, Fragment Shader, associate that with our GL object, and then say, use this program. Again, boilerplate code for us, all of this stuff. Next, we have our 6 lines for sending this to the GPU, or loading it into the GPU format, I should say. 3 lines here, create a buffer, bind that buffer to the array buffer object, send the vertices to this buffer. Right, so basically, this var buffer ID is going to be what is identified as your vertex object. Took me a while to realize that this buffer ID is kind of the important thing here. And so we're going to flatten our vertices. Vertices, again, are our points here. And we're going to do that. Okay, so we have our vertices there. Now we're going to associate the position from the shader to our buffer. So here we've created our buffer. Now we want to get the information from our shader code and construct it into a way that the GPU is going to understand. So some magic numbers here again. This is all going to be pretty straightforward until we start getting a little bit more complicated. But kind of just take it on faith for now that these 6 lines are what you need to draw a single object with a single color. We saw last time that if we wanted multiple colors, we had to add in a bit more here, right? And then call render. And again, we're just calling render one time. And here in render, I've got some extra code here for you to look at, and we'll look at it here as well. But just as a reminder, first thing we do is clear out the buffer, or sorry, we clear out our viewport with whatever color we've set. Here it's black. And if we go back here, background is black, triangle is white. Look at our shader code. Triangle is white. Again, these are all full values of color. So red is full, green is full, blue is full. 255, 255, 255 if you're thinking in integers. So this is going to be white. Look at our background color. Our clear color is black, 0, 0, 0. I could change the background color to be green by updating this value here. So again, this is red, green, blue. Now it's green. Go green, go white. All right, so we're drawing triangles here. Again, a full standard program. Everything is working. Everything makes sense, hopefully. All right, so last but not least, some stuff that's happening under the hood. Flatten is taking that JavaScript array. I should probably mention that so you know what's going on here. This flatten vertices, we talked about this last time, but it's taking this vertices array and flattening it into a float 32 array. And that's what the GPU is going to understand how to use. And then basically these numbers will be like indexes into that flattened array. Okay, so then we're going to render it and we're going to get a thing. Okay, so this is where the fun begins. Haha. Right now I have it drawing GL triangles, and I'm saying 0 to 6. And if we remember from last time, these two variables here, this is the start. So where in your buffer are you looking for the vertices? You could have an offset, right? So this could be, I guess let me step back for a second here. This render function is going to be called for every single object we're going to be drawing. And generally, we only need to call this function once. Okay, so if I've got one triangle, if I have 100 triangles, I could call this function one time and that would be enough. I guess I could call it, I'm explaining this wrong. Sorry, let me drop back for a second. We're only going to really have one array of vertices that we're going to be dealing with, more or less, at least for this class. This function here, we're going to call it, again, we're going to say, what is the primitive that we're drawing? What is the index into this big, long float 32 array that we're starting to draw? Right, so when we call flatten on vertices, this is going to be an array of 0, 1, 2, 3, 4, 5, 6, 7, right? So these are all just taken from an array of 2D objects into a flat array. This is going to be where you're starting, and we've been calling it a 0 because we only have one object we're dealing with. But I could have multiple objects if I want, basically, if that makes sense. And then the next parameter is how many vertices are in your object. Right, so here we're saying there's 6, and this is going to do, honestly, here it's not doing anything really interesting because we're trying to say, hey, make a full square, but it's not doing it. I could change this to 3, and it's going to do the same thing because it only really knows how to draw this one triangle with triangles. All right, so let me comment this out for a second here. Now let's look at the triangle fan. No, we want to look at the triangle strip first because otherwise it's going to be a little bit more interesting. So this is a triangle strip. Now a triangle strip is going to draw the first triangle, and then every additional vertex that you add on is going to be combined with the previous two. So I forgot to add in the image that I want. So it's triangle strip and fan. I think the search term I want here. Sorry, I had a picture up and then I lost it here. But let's look at this guy. Again, I know how to do this in one click. Why does it take me 30 clicks in class? Okay, so triangles make sense, right? Vertex, 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 close it off, you have a triangle. Vertex, 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 close it off, you have a triangle. The triangle strip, you're going to define your first triangle, okay? And then every extra vertex gets combined with the prior two. So here I'm going to draw 0, 1, 2, triangle, close it off. Then I'm going to add another vertex. This triangle is 1, 2, 3. I add another vertex. This triangle is 2, 3, 4. Another one, 3, 4, 5. So basically we're just having a series of triangles where every next vertex adds onto the prior two. Does that make sense, I hope? So basically every time you tack one on, you close off that triangle. So this is a triangle strip. Make sense? I'm going to draw it out in paint here in a moment too to show you how we actually get to the shape. The fan looks kind of like this, where the first vertex is your root, and then every two, or then you add on two, you get a triangle, and then you add on another vertex, and you reference that initial point. So the difference between these two is that in the triangle strip, you add on the prior two. In the triangle fan, you reference the prior one and the first one. So this is kind of how you get like a fan type of thing going on. And these are going to be our three core ways to draw things. And if you want to get into like modeling shapes, that's going to be called triangulation or tessellation. It's going to be figuring out how you can algorithmically turn these shapes into curves, basically, or objects. And we looked at this last time, right? We pulled up some images and we looked at different polygon representations. But here, how do we get to this? This is kind of an interesting thing here, right? We're trying to get a square. And we gave it 4 points for a triangle, or for a square, and it said, hey, draw a strip, right? Draw a strip. So what this is doing, and this is what I pulled up just to make sure that I do this correctly, because I didn't want to screw this up and get everybody confused. So we have a triangle strip. So we're going to draw our first triangle. 0 to 1. I'm going to do this backwards because otherwise it's going to try to do that. And then we're going to close off the triangle. All right, so here is triangle 1. Our triangle strip is then going to take every next vertex and combine it with the additional 2. So 0, 1, 2, and then the only other vertex we have left is 3, right? So I'm going to draw a line here, and then we combine it with the prior one, and then we get something like that. It's going to fill it in because it's done with its vertices, and you get something like that. Now, how would we get this whole thing filled in? Well, we need to add another vertex and go back to 0, basically. So that's our triangle strip. Questions at all on this one? Are we good with this idea? Again, it takes a little bit of mental leaps to get to this point in a way. You have to start thinking, okay, where in the array are we? Which vertex is going to be used next, that kind of thing. And you're doing all this manually right now, but this is something that you can algorithmically define. And again, when we get way down the line, there's tools that will help us with this too. All right, lines are gone. Now, let's look at the triangle fan. And what we're going to see here is a full square. Yay, that's what we wanted, right? Again, I could have just defined 2 triangles here, right? Triangle 1, triangle 2, but I could also do it with the fan. So let me show you a little bit of a diversion here. So triangle fan. Should I draw this in the right order again? Fan is based on the first point, which is our bottom left one, right? So we're going to draw our first triangle. It's going to look very similar. Here's triangle 1. And there we go. Then our next vertex is going to reference the prior vertex and the original one. And it's going to get dragged because that's what it wants to do today. So then we get the whole thing. Paint. There we go. Pop, 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 pop. Ah! No. Good enough. Good enough. This is filled in too. I guess I could probably do that. How's it going to work? There we go. So we get our square. Triangle fan references the first point and the prior point. Okay. But, Professor, you might say, can't we do that with GL triangles? And I would say yes. Let's go ahead, comment this guy out. Let's add in 3 more vertices. So basically, start at the bottom left, go to the top right, and then go to the bottom right. So I'm going to save, refresh, and then we still have the same thing. We have a square. We get the same behavior, but what's the difference? And why is a triangle fan, in this case, better? And you might look at this and say, well, it's a super trivial program. You're an idiot. Why are you wasting your time with this? And I would say, you've added in 3 extra vertices or 2 extra vertices, right? So here are 1, 2, 3, 4. Yeah, triangle fan uses less data. Exactly. This is 1 square. We've added 1, 2, 3, 4 extra array elements. That's 4 32-bit floats that are taking up memory in our application, right? On a small scale of 2 triangles, that's nothing. But again, scale this up to a actual model and you'll see that that kind of waste can really start to kind of bubble up. So that's why we have these objects. Basically, the point is try to conserve vertices because if you get over the limit, you're going to have a very, very bad time. Very slow programs. All right, let's look at lines just very quickly for fun. So there's your GL lines. GL line strip. Basically, it's going to follow very similar patterns to triangle strip. It's going to just try to connect things together. And we'll talk about points and lines and all that fun stuff in a later lecture. But basically, we have that available to us. But we've basically triangulated a square based on our primitives we have. And it just took us 2 triangles or 1 triangle fan to do it. Okay, where are we at? Yeah, there we go. All right, questions at all on that? Otherwise, we'll talk about the gasket. Again, this is in the demos folder on the GitHub link. I guess I should mention too, since I made a big deal out of this the last time, P5, yeah. This is moving pretty quickly because this is actually a whole image being drawn. It's not single ellipses or circles like it was the last time. So I'm saving a lot of processing power because this is all one image being scrolled around. Just wanted to point that out as well. Alrighty. So if we are all good with that, then let's talk about fractals. Fractals are fun and they're interesting and you can do lots of really cool things with them. What a fractal really is, though, it's just a recursively defined image. So it is a procedurally generated something. And there are a ton of fractals out there, right? If you've ever looked at any like computer generated art, there's a lot of people that like using fractals. There's actually, I could have swore I had this. There's a Mandelbrot 3D fractal cave WebGL, WebJ, GJ, Mandelbulb. Yeah, here it was. So you can do all kinds of really crazy things with fractals. And this is not what I was thinking it was, but there was a WebGL demo where you could like kind of explore a 3D generated Mandelbrot cave, and it was crazy what you could do with it. I could have swore that was the search term for that, but if I find it, I'll come back to that. But fractals, algorithmically generated art. We're going to be using the Sierpinskiing gasket, which is basically just a series of triangles that have been cut out of a big triangle. So you're going to start with that triangle.js from our first in-class assignment, and you're going to cut out the middle of it. So we're going to basically figure out where the halfway point on each line of the triangle is, the bisector. We're going to connect them, and then we're going to get our triforce here. And then if we're going to use ancient 4chan lingo, we could put some of these together and we could triforce and it would be super fun. But instead of being as horribly cringe-worthy as that, we're just going to keep doing this over and over and over again on a single triangle. So we're going to connect these bisectors, we'll connect these bisectors, we'll connect these bisectors. And we're going to keep recursively cutting it out. And then you're going to get something like this. And basically when you see this, all that means is that we've given it a particular stopping point. So let's take a look at our gasket here now. Wrong Alt Tab, not that one. Chapter 2, gaskets. Okay, so this is your homework assignment. There are other gaskets in there as well. There's ones that are filled in. It's gasket 3. Got one with multiple points. Gasket 4. Got 3D gaskets. Then there is gasket 5, I believe. Nope, not gasket 5. Was... Sorry, I should really stop closing tabs when I actually need to use them. Gasket 4. It was 1v2 is what I was thinking of. Okay. It's basically defined a little bit differently. 4 is the stopping point. I thought there was a 5 for some reason. Maybe I'm misremembering. Anyway, enough jabbering. So we're going to look at this gasket, and we're going to see a couple of different things in here. So there's some difference in the HTML, and there's some difference in the script file. But the only real difference is we're defining the point size. So this GL underscore point size, this is another one of our WebGL variables that are just there by default. We're setting it to 1. Right, so we see, this is not my local one. I want my local one, please. GBSU, 367, graphics, chapter 2. Don't do what I'm doing. I'm just going to modify the GitHub file directly. Let's make that a bit bigger. Okay. So gasket 1. I'm going to change this point size to 5. What's going to happen? Whoa, it's bigger. Almost like a homework question. Cough, cough. We are drawing this thing with GL points now. So I'm going to go over to our application code, our JavaScript file. Instead of gl.triangles, yep, I just had this thing in my throat. I don't know what it was. So our gl.drawArrays function now, instead of gl.triangles, we're calling gl.points, which makes sense. These are pixels that we're drawing here, basically. Instead of having 3 vertices, a point is going to have 1 location. So it's going to have 1 xy coordinate. It's also going to have a size and a color, but that's going to be your fragment in there. So GL points, 0, points.length. Before we call this directly by hand, right, we did like 0, 3 or 0, 6. See this points.length, you might think, oh, we're finally using this var points variable, which is good. Yes, we are. Basically what's happening here is that we're creating a global variable of all these points, and we're just going to let the drawArrays function use that variable, and we're going to take advantage of that length property instead of having to manually figure out how many points we want in there. Like if I change this to, 10 instead of points.length, comment out. It's going to look way worse. You can kind of see them. There's my points. Actually, I'll make the pixel size a little bit bigger so we can see them. There. Here's my 10 points. They look kind of randomly scattered there, right? Again, that's because we are, mucking about with recursion. Hey, pop quiz for those of you that remember your Java and programming classes. What do we need for recursion? I guess what's the one most important thing to have in a recursive function? Anybody remember that one? End condition, thank you. If you do not have an end condition, you can't end it. Otherwise, it's going to go on forever. Yeah, end condition, stop condition, exit condition, whatever you want to call it. That's how it's going to be. And if you do not understand recursion, I can give you the tip that my undergrad C++ professor gave me many, many years ago. Find yourself a concrete wall and keep hitting your head against it until you understand recursion. And that's how I learned recursion, and it worked pretty well. All right, so this script that we're doing here now, they fixed it, right? Okay. We're drawing points, and we're going to be doing some recursive calls. So there is a little bit more in here than usual. So let's walk through this a little bit. So we're going to specify how many points we want to have. And we're going to basically do some extra stuff in here, yeah. So this num points is referenced later on when we're trying to figure out how many points we want. Now, there's some differences in here. I would highly suggest reading through this again. It's part of your homework, so you're going to have to understand it anyway. We have our boilerplate code here. We have our vertices. We have some new stuff, but then we have our pretty standard Webgl code here on out, right? So our viewport, our clear color, our program, our buffer binding, this is all identical to what you have before. So don't look at this and say, oh my God, that's a massive program. This is all the same stuff. The difference though is that instead of vertices, we're using this points array. And down here, we're using points.length instead of a number, a magic number, basically. Try to avoid magic numbers if you can. I know these all look like magic numbers in here, but that's just initializing the API. So, boilerplate code. The interesting stuff in here, though, is that we're defining our base triangle, right? So -1, -1, 0, 1, 1, -1. That's going to be our standard triangle, right? So from here to here to here. So our standard big triangle. Let me do this maybe. Here to here to here. Basic triangle. And again, what we're doing here is we're actually computing the bisectors. And all that means is that we have some mathematical functions where we're going to be mucking about with our vertices. So figure out a starting point. We're going to add some array points together, and then we're going to scale them, and then we're going to call add again in here. Basically, all we're doing is calculating the midpoint on these two lines. So we have these add, we have some scale calls. These are all part of the math libraries that we have in there. And this is kind of particular to this gasket call. Now you might look at this and say, okay, you're not explaining this in great detail. Yeah, I kind of want you to, maybe try to, maybe not figure out, but kind of understand that we're basically just doing matrix math with these add calls and these scale calls. In this algorithm, honestly, it doesn't matter. This could be any algorithm, right? We could be doing a Mandelbrot algorithm, in which case it would look differently. The one that we're doing here is we're just doing some standard trigonometric calculations. Figure out the midway point on a triangle edge. It could be figure out the center of the triangle for like a Voronoi diagram. It could be figure out what the farthest triangle away from us is. The point is, this doesn't necessarily matter. It's just an algorithm. The interesting thing that we're doing here from WebGL's perspective is that we're figuring out these points. We're adding it to our array of points. We're going to continuously calculate it. I guess I should step back a little bit. This one isn't recursive. The next one's recursive. This is just a for loop. So construct a list of vertices. and then display it. Right, so if I change this num points to be 15,000, you get a little bit more fidelity, right? I've got more points. Could change it to 55,000, even more. 155,000. 2 million. It's starting to look like normal triangles. But I've got a crap ton more vertices here. Again, don't get hung up on the actual algorithm. Kind of want you to read through it and try to figure it out and understand it, but it's replaceable with whatever you want. One other point here too before I let you go for the day. We're doing something kind of not great here. All of this code is running on the CPU. So this is JavaScript code that's running. Right? We are not using our graphics card. Remember that our graphics card is built to handle matrix operations. Doing all of this in JavaScript is defeating the purpose of having a graphics card, right? So what we want to kind of move towards when we get later into the semester is we want to take all this code, put it into our shader. But in JavaScript, it's a lot easier to understand. So yeah, gasket 1 is what I'm going to want you to modify for your homework. Gasket 1v2 it's going to be our 1v2 our recursive one? One of these is recursive. This is still, yeah. There we go. Sorry, gasket 2 is the recursive one. I was getting ahead of myself. Basically, you're going to have a call to divide triangle. Divide triangle is going to be your recursive function. Then you have your base case or your end case. So, sorry, I was off by 2 scripts, but you guys get to start out with the simple for loop. All right, that is probably good for today. Anybody have any questions at all? So kind of what we covered is triangulation of a square by hand. We looked at some of the different polygon types in WebGL, got you all set up with a full program, and now we're starting to look at the gasket. And what we're going to start off with next time is we're going to get into colors a little bit. So if we're good with that, look at that. I ended right at the time that I did 2 years ago. Impressive. All right. Hope you all have a wonderful day. Thursday will be on Twitch again, so I'll see you then. Thank you for a good class and for interacting. And yeah, Serial, I will try to get that thing set up that we talked about before class. I really like that idea, so thank you for that. And I guess if any of you kind of tuned in late, basically the point was, yeah, Thursday is going to be Twitch. We're only going to do Zoom when you have in-class assignments to do. But what I'm going to try to get set up for Thursday is I'm going to try and get my streaming software set up so that we can have like a private audio channel that only I can hear and Twitch can't hear. That way you can talk and interrupt me. I'll just kind of parrot your question back to the class. Yep. Okie doke. Well, I will see you all Thursday. Have a wonderful evening. And make this a Twitch lecture. Seriously, the worst interface in the world. All right. Bye, everybody. See you then.